Hi, this is Nathan Smith with Fresno Pacific University. This is a voiceover PowerPoint video for my students in Visalia and North Fresno on Chapter 3, Optimization Techniques and New Management Tools. Okay, so why are we interested in optimization? Well, we can think about examples. For consumers, consumers tend to maximize utility, you could say, by purchasing some optimal combination of goods. They choose what they want to buy to match. Utility is basically an expression here for what they like, preferences. So, even more relevantly to the course, so the consumer behavior is relevant because, of course, businesses have to have some idea of guess what consumers want, what consumers are going to do. But even more relevantly, firms maximize profit by producing and selling an optimal quantity of goods. Now, maximization and optimization are closely related. Optimization could be maximization or minimization. It's basically getting to some extreme, trying to push some variable to the extreme limit that can be achieved. So it might be to a maximum, so that's how optimization and maximization are related. So profit maximization is an example of optimization. And obviously one that's very relevant for managerial economics. You might also think about cost minimization. So if for some reason the quantity you're going to produce is already fixed, you might just think about, well, okay, what's the cheapest way that we can produce this? Or what's the cheapest way we can produce 1 unit of this? So those are examples of optimization. It's still rather abstract examples. So you could then give examples of profit maximization, take it further down, which we will. But so this is why optimization is relevant here. Now, optimization is kind of a mathematical concept. So we look at economic relationships. If we want to engage in optimization, then we need to express them mathematically. So in this case, we are expressing total revenue, TR, as a function of the quantity that's produced and sold. So in this case, so we say TR equals 100Q minus 10Q squared. Notice we're not saying anything about cost right now, just revenue. So what does this depend on? Depends on demand. So there's some kind of demand curve, and so as you sell more, if it was just TR equals 100Q, that would suggest the demand curve was flat. But since it's minus 10Q squared, well, what's going on there? Well, what's going on is that the price you can charge falls as you sell more. So total revenue is not proportional to Q. It's a more complicated function of Q, which it may either rise or fall as Q rises. This as shown in the graph. So it rises for a while, then it falls. We have it expressed as an equation, a table, and a graph. All of them say basically the same thing, but this is a mathematical expression of an economic relationship. Okay, total, average, and marginal revenue. So these are important concepts in optimization. Especially marginal revenue. That's the most counterintuitive. In this case, total revenue we've already seen. Average revenue is total revenue divided by quantity. I mean, in this case, you can see total revenue equals PQ. Average revenue equals TR over Q, and marginal revenue. But that's just the same as P, right? Because if you divide PQ divided by Q, then you get P. The average revenue is just the price. Marginal revenue, this is very important. This is the change in total revenue over the change in Q. Mathematically, this is actually calculus, so this course, you want to kind of... it might be helpful to be willing to dip your toes into sort of baby calculus. Okay, so we can see how they're calculated here. So far we're not actually using calculus, we can just calculate how large the step is here. So okay, one more unit. Average revenue falls, and this basically tells you what the demand curve looks like. So this is basically how the price is falling as the quantity increases. So if you're selling 6, people are only willing to pay 40 for that. Marginal revenue decreases faster, and you notice that here, if you say, okay, 2 times 80 equals 160, 3 times 70 equals 210, 4 times 60 equals 240, so you can see where the total revenue comes from if you know the average revenue curve. But then, the marginal revenue curve you can get by comparing 160 minus 90, well, that's 70. 210 minus 160, that's 50. 240 minus 210, that's 30. 250 minus 240, that's 10, and so on. Negative 10 down here. So all these curves are related to each other. I mean, if you knew total revenue, for example, then you could derive average revenue and marginal revenue from it. If you knew average revenue, you could derive total revenue from it. I suppose you could even, if you knew this 0 and then you had marginal revenue, you could just add those up and then you'd get total revenue. So these are all related to each other in a sort of necessary, logically necessary way. Okay, so this shows how you get total revenue from the equation. How you get the actual values of total revenue from the equation. Again, this is pretty simple. All you're doing here, where's my mouse? There it is. All you're doing here is plugging in 0, 1, 2, 3, 4, 5, 6, plugging in the values of Q. So you've got an equation in Q here, you've got Q over here, you plug in Q, then it gives you total revenue. So you plug in 100 times 1 minus 10 times 1 squared is 90, 2 times 100 times 2 minus 10 times 2 squared is 160, so on, all the way down. So that's the total revenue schedule of the firm. Okay, so then total revenue curve of a firm. This represents the same as a curve, so we have the same values, the 90, the 160, the 210, the 240, the 250, the 240 again, graphed against this. So you, again, as a matter of getting used to seeing the same thing expressed in equations, tables, and graphs, same information. Okay, now we saw up here, we saw total revenue, average revenue, and marginal revenue in a table form. Now we can represent this graphically. And one thing to note here is that we represent total revenue on one graph. We represent average revenue and marginal revenue on a separate graph. And the reason for this, these are actually measured in different units. Total revenue is measured in dollars. Average revenue and marginal revenue are measured in dollars per unit of the good. So it wouldn't really be proper to put them into the same graph. But you notice average revenue slopes down, and that is actually your demand curve. So this chart has the same units down here, quantity, same units on this axis as well. Price, or dollars per unit of the good, and the average revenue. So that's basically price. It's the same units as price anyway. Average revenue, this is really the price. So this is essentially your demand curve that you have graphed here. Marginal revenue is twice as steep as the demand curve for this special case where the demand curve is linear. In the general case where the demand curve might have any shape you want, then marginal revenue is much more, well, you can only basically know what it is through calculus, but in textbooks at least we'll often use this linear demand curve, and then in that case you know the marginal revenue curve is just twice as steep. Or you could think about it by saying, well, it actually looks a little bit different, because we did something over there. We said this was 90. We could put 1 up against 90. Well, this 90 is the average over this stretch. 70 is the average over this stretch. 50 is the average over this stretch. That's how this graph is related to the curve that we had before. But you actually aren't plugging in exactly the same values here. And so this, in a sense, this is actually truer than the table, because it's showing you the whole curve at each point along the way. But yeah, don't worry too much about that. But yeah, the main thing is so marginal revenue and average revenue are related, and we'll think more about just how this is sort of an introduction to how you can draw that chart. Okay, we can think about cost in a similar way. So total cost, average cost, marginal cost. Now here again, if you take total cost divided by quantity, you get average cost. So 160 divided by 2 is 80, 180 divided by 3 is 60, 240 divided by 4 is 60, and so on. And then marginal cost is just the difference between that and that. So 140 minus 20 equals 20, 160 minus 140 equals 20, 180 minus 60 equals 20. So these are actually derived in different ways. Yeah, total quantity, and then we have kind of the total quantity over Q is average cost, marginal cost is the change in total quantity over the change in Q. So here, so this is just same information as there, I think. Yeah, just represented as a table. And then here we represent it graphically. And so here we have total cost sloping up like this. Now let me see if they do the same thing. Yeah, so the 120 now doesn't really correspond exactly with the unit 1. The 120 is actually placed like midway between 0 and 1. This 120, because again, I mean, the 120 should really be the average of the marginal cost over this this gap. So it's a little bit confusing exactly how the graph relates to the table, but don't focus on that. The key here is so why is marginal cost important? Well, for a couple reasons, but for now, one we can say is where marginal cost cuts the average cost curve from below, that's where average cost is minimized. So if marginal cost is less than average cost, that means that average cost is falling, because each unit at the margin costs less than the previous units on average did, so that lowers the marginal cost. If marginal cost is the same as average cost, that means that average cost is flat, and since marginal cost here is cutting average cost from below, that means this is at least a local minimum, and in this case a global minimum of the average cost function. MC equals AC at lowest cost. This represents it for the U.S. steel industry. Did we see that? Did they give us the graph of the table of that before? Huh. I guess not. Oh, yeah, they are. Yeah, here's the table form. So this is the cost schedules in the U.S. steel industry in the 1930s. So this is from an important academic paper. Somebody went through and made an estimate of what the total average and marginal cost schedules of the U.S. steel industry were. You notice in this case, it's a little bit different from most of the cases we've looked at. Marginal cost is level, and then average cost keeps falling. So here you have major economies of scale in this industry at this time. Total cost keeps rising, but not proportionally with the quantity. Okay, so now we're kind of bringing it all together here. In particular, bring together, and here, in spite of what I told you, they're putting total cost and marginal cost together on one graph. So they're kind of treating total number of dollars and the total number of dollars per unit as the same quantity. And so here we have total revenue, total cost. So we've seen these before. Now, think about where would you maximize profits. If you wanted to maximize profits, where would you want to put? What quantity would you want to choose? Well, if you choose over here, well, total cost is more than total revenue. That doesn't seem very appealing. Well, here cost kind of starts to level out, so that's good. revenue keeps rising steeply, cost kind of levels out, so that's good. Now you could produce here you'd break even, here at B. Total revenue and total cost are the same. Is that good? Well, it's better than taking a loss, but it's not that good because it means you're not making any profit. So, okay, now suppose we move up to D. Well, here again we're breaking even, but not making any profit, so that's not particularly good. Now, here at C, now this here total revenue is above total cost, so that's good. That's what you want. And now you can see you're making profits there, so it's relatively appealing compared to most points on the curve where you're either taking a loss or at B and D or not, or you're just getting zero. You're breaking even. But now, okay, if you look at this curve, and it's not that obvious just to eyeball it, where the gap between these two, that's really what profit is the gap between these two curves. It's not that obvious where that's maximized. Well, this drawing kind of helps you because they show a place, they show you where these two tangent lines, two parallel lines are both tangent to the two curves. So in other words, the curves have the same slope. And that's where you get maximum profits. However, it's very unclear from this. It's somewhat more clear if you take these marginal curves. It's marginal revenue. Again, marginal revenue is just steadily falling. Marginal cost first falls and then rises, and this is where marginal cost cuts marginal revenue from below, and this is the key. It's where marginal revenue equals marginal cost. That's where you're maximizing profits. I mean, there's a couple assumptions there, such as that marginal cost must be rising and marginal revenue must be falling. Marginal revenue is almost always going to be falling because demand curves, it's almost always going to be either level or falling, because demand curves always slope downwards, so you're not going to you won't be getting more marginal revenue from the last unit than you did from the previous one. But marginal cost, it's not necessarily rising, but it could be level, and you could still have marginal cost. You could actually have marginal cost cut marginal revenue from below, even if marginal revenue was falling, if it was falling less fast, or even if marginal cost was falling, if it was falling less fast. But in any case, where these two curves are equal, and you can kind of see it this is where you maximize profits. And you can kind of see it if you think about, okay, if you're producing unit 2, well, you're incurring some marginal, if you start producing more, you're incurring marginal costs, and you're earning marginal revenue, but you're earning more revenue than you're paying in cost. So that's worth doing, and that's true as long as marginal revenue is higher than marginal cost. That means on the last unit that you make, then you're going to be making more money on the margin than what you're losing in cost. But when you get to C star and then you start pushing beyond that, well, now you're incurring marginal costs that are greater than the marginal revenues that you earn, so that reduces your profit. Now we see profit here. Profit is just the gap between these two curves. So in this case, it's the gap in the sense that it's the blue curve minus the red curve. It's total revenue minus total cost. That's profit. It's always revenue minus cost. And so you see profit falls initially as you produce the first unit, but then it starts rising, then it rises some more, then it starts falling. So it's maximized here at C prime. So this, in a nutshell, this is profit maximization. And you notice these marginal curves, these were a little bit difficult to understand. Why do we pay so much attention to them? Well, they're crucial for optimization. They're more important, really, than the average curves, which are a little bit easier to understand, but their average curves aren't going to get you optimization. Okay, well, now we've looked at a particular case of optimization. Now let's think about it more generally. You can think of optimization as in several steps. First, you define an objective function mathematically as a function of one or more choice variables. So choice variables are things that you have under your control. The objective function is what you want to get. And so you define how what you want to get is related to the choice variables that you're under your control. Obviously, this isn't that easy to do. I mean, in this case, we've assumed that we just know what the demand curve is and we know what the cost curve is. For real businesses, they usually won't, or at least they won't know that easily. They'll have to exert a lot of effort to figure it out. And usually, even if they do exert a lot of effort, they won't know for sure. But for now, we're just going to assume that we somehow know that. Then next, define one or more constraints on the values of the objective function and or the choice variables. So this is things like, sometimes there are no constraints exactly. Certainly if you're a consumer, you've got a budget constraint. So, and if you're a business, there may be some limit on how much you can borrow, for example, or how many employees you're able to hire without coming under new regulation, whatever. There might be various constraints that you face, and then what you want to look for is the value of the choice variables, maximize or minimize the objective function, depending on whether the objective function is something good or bad. The objective function might be cost, in that case you want to minimize it, or it might be profit, in which case you want to maximize it, while satisfying all of the constraints. So it has to be feasible, and has to maximize the objective function by choosing the choice variables. That's optimization in general. Now, this is a counterintuitive example. Pollution. People think pollution is bad, so to ask what's the optimal level of pollution sounds almost like a paradox. But you might say, well, of course, the optimal level of pollution is 0. But economists say, no, it's not 0, because the types of activities that pollute also create economic value. So if you were to reduce pollution to 0, you'd also be eliminating, a huge set of economic activities and all the value that they produce. So you don't want to do that. But on the other hand, at some margin, it's not worth producing any more pollution, because it will presumably have marginal benefits, have at least some benefits, otherwise people wouldn't do it. But at some point, the marginal cost may be higher. So you can think of this as the marginal benefit curve, marginal cost curve of pollution. The assumption here is that pollution gets costlier as there's more of it. That may or may not be true, but it almost is certainly true that marginal benefit falls like this. And in any case, what you want to look for is the place where marginal benefit is equal to marginal cost, and that's the optimal level of pollution. Okay. I'll talk about these ones in class, but I may do another video for the appendix.